Welcome. We'll look at Cauchy Euler second order differential equation. So here we have that A, B, and C are numbers, scalars. X is the independent variable. We're going to assume that X is positive. We could also assume X is negative, but we'll assume X is positive. And we're going to develop a method for solving such a differential equation by turning it into a ordinary differential equation there with constant coefficients. Right now we don't have constant coefficients. We have x squared multiplying y double prime and an x multiplying y prime. So that's not those are not constants. So let me give you an example of such an equation. X squared y double prime plus 2xy prime minus 6 times y. And it's we're looking at the homogeneous, right? We're just looking for fundamental solution set. And suppose somebody said, well, let's suppose that we could find a solution in the form where y is equal to x to a power r. We don't know what that power is. So is this, will this assumption for a solution work? And if so, then what would r be? Well, as always, if we make an assumption about a solution, we're going to see what would have to be true about r in this case for us to have a solution like this. So we differentiate with respect to x once, twice, and then we plug that into our differential equation. So you get x squared times y double prime plus 2 times x times y prime minus 6 times y. And that's equal to 0. So as you might see, simplifying, we get multiplying these. Okay. We will always get a factor of x to the r. And since we assumed x is positive, we can just factor out x to the r. Well, let's just do it that way. And so we see that x to the r is not 0 because of this condition. So it must be true that this polynomial, this quadratic, in r must be 0. And we go ahead and try to find the values of r that solve this equation. And here I can either use the quadratic equation, or I can just factor for this simple problem. So I see two roots. One root is -3, and the other root is 2. So apparently, our solutions we assumed that looked like y is equal to x to some r, and the r's that would make this work are -3, and we get another solution where r is 2. So this is a fundamental solution set to our differential equation. You can confirm that these are indeed solutions. You can compute the Vronsky to see that these are in fact independent. So you get 5 over x squared, which is not 0. Of course, what's going to complicate matters is that the roots of a quadratic, are not necessarily real, or they might be repeated roots. So you have to learn what to do in such cases. So I'm going to go through all the different cases, give you examples for when you have real distinct roots like we did right here. You have real but a repeated root, and you have then imaginary roots that come in conjugate pairs. And then after doing those examples and looking at the formulas, we'll derive the method by which why this works more formally. All right. Okay, so what we're going to do now is look at a more generic, like a general form of the Euler, Cauchy-Euler differential equation, second order, homogeneous, assuming x is positive. So you would assume that your solutions look like x to some power r. You differentiate twice, and you plug the derivative. So here's a second derivative back into the original differential equation. And again, if you simplify, you're always going to get an x to the r term, factor rather, in every term. And since we assume that x is positive, in particular it's not zero, this means that this quadratic, this associated quadratic, this kind of characteristic equation for the Cauchy-Euler differential equation must be zero. And you want to find the roots. So you want to, this is an important equation. You can remember it either this way or this way. But let's say it's the associated characteristic equation for a polynomial, say, or our Euler, Cauchy-Euler type of differential equation. And then you would want to find the roots. Now, of course, you're going to have complications, right? Because we could have real distinct roots. Okay, we could also have real but repeated root, or we can even have complex roots that would come in conjugate pairs. So let's look at each case, maybe write out some formulas, and then we'll come back and derive why these formulas work. So we'll do the three cases, right, for the roots. An example of each. So case one, you have real distinct roots. And then since they're distinct, R1 is not going to be equal to R2, and these are real numbers. Okay, so then your solutions to the Cauchy-Euler equation is going to be x raised to the two different roots. Okay, so here's an example. So you can either go through the derivation where we assume that a solution to this equation is in the form x to a power, or you can identify that in this equation, right, your a is 1, your b is 3, and your c is -3. And then go straight to the characteristic polynomial for the associated to this and find the roots. So I'm just going to go to the characteristic equation where a is 1, b is 3, and c is -3. You simplify and either use the quadratic equation, or in this case it's just easy enough to factor. So the two roots are -3, the two distinct real roots are -3 and 1. So our solution, or our fundamental solution set to this homogeneous equation. All right, so next we just did the case of real distinct roots. So case 2 is going to be obviously real but repeated root. So here we have real repeated root. So we're going to get that our root is R1 and R2 are the same, but real. We just can call that R. So in this case, your fundamental solution set will be x to the r, and then y2. Now here you can use reduction of order to prove this, but there's maybe a better way to look at it. It's going to be x to the r, and then you multiply by the natural log of x. So you can, you'll see that this is still a solution to our equation, and it's linearly independent from y1. Okay. So in the case of repeated root, you just still x to the r, but then you have to multiply by this factor, which is natural log of x, which again, remember we're assuming x is positive. So that's defined. Go through the derivation, but here we have a is 1, b is 3, c is 1. So I can write down my characteristic equation, and we get, okay, so indeed, here we get that r is -1, but it's has multiplicity 2, so it's a repeated real root. So then the claim is that the first function that works here is x to the -1. The second function that will work be x to the -1, but multiplied by natural log of x. And these, again, you compute the Vronsky or something to confirm these are independent. You can even derive this using reduction of order, the second solution. So now the third case, it would be where the roots of your characteristic polynomial are imaginary. So case number 3. And they have to come in conjugate pairs, right? So let's call the real part alpha, and let's call the imaginary part beta. So then your fundamental solution set would look like this. X to the alpha times, say, cosine of beta times log x, and y2 would be x to the alpha, and then sine of beta log x. Okay, so then that looks strange, but we will derive why this works after the examples, and we go through the 3 cases. So here's an example. Constants are 1, and b is -3, c is 13. So I'll go straight to my characteristic polynomial, which we can always, if you forget, rederive it by simply assuming y is equal to x to the r and differentiating that a couple times, plugging it in. And now I'll just use the quadratic formula here, so r. So indeed, here we have our roots, our complex conjugate pairs. The fundamental solution set to our Cauchy Euler homogeneous equation. y1 would be be x, the real part, that's 2. The imaginary part is plus or minus 3, we'll just use 3. X squared times cosine of 3 times log x. The second solution be x squared and sine of the imaginary part times log x. So in summary, you have Cauchy Euler equation, homogeneous, assume x is positive. Okay, we can derive the characteristic polynomial here using the assumption that y is in the form x to some power r. Okay, we find the roots. And then we had 3 cases. We have real distinct roots. This, I guess, the simplest case with our fundamental solution set. We had real but repeated root, in which case we get a second independent solution here by multiplying by log x, multiply the x to the r by log x. And finally, we had the roots of our characteristic polynomial being complex conjugate pairs. So that's the summary. It's the formulaic road. Okay. Now what we want to do is actually derive why these formulas work. So why do these formulas work? What we're actually doing is we can think of it as changing the independent variable. X we're going to assume is positive. Let the independent variable x be expressed as e to the t, right? So x is positive, the exponential function is positive. So this is sensible. Okay, and then we're going to try to replace all instances of the independent variable x with the new independent variable t. And that's going to turn this Euler equation into a second order equation with constant coefficients where in the new independent variable t. Okay. So in order to do this, let's write this explicitly. This y double prime is the second order derivative of y with respect to the independent variable x. Y prime is the derivative of y with respect to x. Okay. So now we're going to need to compute dy dx in terms of dy dt, right? Because we want to introduce the derivatives of y with respect to the new independent variable t. So it's just a matter of chain rule here. So derivative of y with respect to x is the same as the derivative of y with respect to t times the derivative of t with respect to x. Now, notice that if x is equal to e to the t, then it's equivalent to saying that log of x is equal to t. So it's actually very easy to find the derivative of t with respect to x. It's just 1 over x. Or if you'd like, since x is e to the t, it's e to the minus t, right? So, okay. So this would be the derivative of y. Let me write. Okay. So let me write dt dx from over here first, and then dy dt. I mean, we don't know what y is, so this is the best we can say. Okay. So then we want to find the second order derivative of y with respect to x. So that's the first derivative with respect to x of the derivative of y with respect to x. But dy dx we already found. So what we're going to do is use chain rule again. So this is equivalent to the derivative of that with respect to t first, then multiply by the derivative of t with respect to x. So product rule for the stuff inside the brackets, differentiating with respect to t, and then times dt dx, which we already determined as like 1 over x or e to the minus t. Okay, so now we have the derivative of y with respect to x can be directly replaced with e to the minus t times dy dt. So, right, so we're going to, in the differential equation, we're going to eliminate these derivatives of y with respect to x in terms of the derivatives of y with respect to t. The second derivative of y with respect to x turned out to be, I can also distribute this, so I'm going to write that as e to the minus 2t. And then we plug that into the differential, our Cauchy-Euler differential equation, where we're trying to get rid of the independent variable. So we get, remember that what we have that y is, that x is e to the t. So we have a times x squared, so that's e to the t quantity squared. The second derivative from right over yonder. Okay, so plus b times x, where x is e to the t, then dy dt, and plus c times y, times the e to the minus 2t is e to the 0, so that goes away. E to the t times e to the minus t, again, is e to the 0, so that goes away. So then we get a times the second derivative of y with respect to t minus the first derivative of y with respect to t, b times the first order derivative, and c times y. Rearranging this, you see that we've turned our differential equation, which didn't have constant coefficients, right? The y and its derivatives were multiplied by some function of x, into a second order differential equation with constant coefficients. And we did that by replacing the independent variable x, which we assumed was positive, by e to the t. And then completing the change of variable. So now we just have, so this is, and we know how to deal with this, second order constant coefficients. We know that we would look for solutions in the form e to the rt, right? So, and the characteristic polynomial here would be a times r squared plus b minus a times r plus c. So that's exactly the characteristic polynomial you would get. So in the case, so let's go through the cases and see why the fundamental solution sets look like what they do. So here we have a solution for y, where y is a function of t, right? The independent variable t, but we want to change that into a function of x. We want y to be a function of x. So in the first case, we have the roots are distinct and real numbers. So then your fundamental solution set for y as a function of t would be like this. But as you note that this is e to the t raised to the power r1. The second solution is e to the t raised to the power r2. And we said that e to the t is x. That's the way we defined x. So this is x to the r1, and y2 is x to the r2. Okay, so that took care of the distinct real roots case. Number 2, again, we have our characteristic polynomial, but this time we're going to have repeated roots. Okay, so the fundamental solution set for where y is a function of t, we know is going to be e to the r, let's say a repeated root is called r, e to the rt, and the second solution is going to be t times e to the rt, because t is the independent variable, and we already learned that for constant coefficient kind of second order differential equation, just multiply the first solution by t to get a second linearly independent solution. Okay, so this is again a function of t, but we want to write y as a function, the fundamental solution set as a function of x. So we just use the fact that e to the t, but also that equivalently t is log of x. Correct this, right? So we get y1 is becomes x to the r, and this becomes t becomes log x, and of course that becomes x, so x to the power r. So that's where that mysterious log of x came in. That factor, we have to use to get the second linearly independent solution for our Cauchy-Euler equation in the case of real repeat group. Okay, so most interestingly, I guess, let's look at the third case, where in your characteristic polynomial, you get complex roots. So when we're solving for y as a function of time, we already know the solution. It's going to be e to the alpha t times cosine of beta t. And the second independent solution is e to the alpha t times sine of beta t. And that came from working with separate differential equations with constant coefficients. Okay, but here again, y1 and y2 are expressions of functions of t, but we instead would like to express these as functions of x instead. So remember that e to the t is x, and t is equivalently log x. So e to the alpha t will become x to the alpha, and t is replaced with natural log of x. So that's where that strange thing came. Those you get that cosine and sine of this log x, right? Because it's really sine and cosine of beta t, but t is equal to log x. Well, I erased the summary. So you can just know based on the characteristic polynomial, kind of memorize what the fundamental solution set is to the homogeneous Cauchy-Euler equation. But we also would like to know the background for how we derive those formulas. And what happened is that we just replaced dependent variable x with e to the t. We completed this change of variable of independent variable, and it changed our Cauchy-Euler differential equation into a differential equation with constant coefficients, which we already know how to deal with. Okay, thanks.